Okay. So okay, so it's lecture 17. And just to briefly recap what we did last time. So last time we talked about similarity of two n by n matrices. And then we showed how if you have enough eigenvalues and eigenvectors, you can diagonalize matrices, which means finding a similarity which turns a square matrix into a diagonal matrix. So the main sort of thing we observed is that if A has n linearly independent eigenvectors, v1 through vn. So this is an n by n matrix. Then you can write A as PDP inverse. So similar to a diagonal matrix where the entries of the diagonal matrix are the corresponding eigenvalues. And the similarity P is just the matrix containing the eigenvectors v1 through vn. Okay, so these eigenvectors correspond to eigenvalues lambda 1 through lambda n. And the point of this was, I did this little sort of toy application to this, skiers and snowboarders example, which was an example of what's called a dynamical system. And the application was that you can model many interesting processes as taking some vector x and then multiplying it by a large power of a matrix. So this is an example of a dynamical system. And I should say that this is people actually use these things to model things like, spread of diseases. But this is obviously a simplified example. But the point was that, understanding the behavior of a to the k times x for large k is kind of a hard problem, right? If I tell you k is like 10,000, then computing this or understanding what the pattern is maybe not so clear. But if you can diagonalize a, then we saw that you can write this as PDP inverse to the k, right? PDP k times, and then all the p's cancel, and this is just p times d to the k, p inverse. And this turned out to be an easy problem. And the reason the left problem is hard is that if you write down a, in general, it may have full entries like this, but if you write down d, it only has diagonal entries, and it's easy to understand how it behaves under taking powers. So, okay, so this, this is what diagonalization achieves in this context of dynamical systems. This is sometimes called decoupling, because when you take powers of a, you have n interacting quantities. Namely the n entries of this vector x as you take powers. Whereas when you take powers of d, the quantities don't interact, right? So you have n one-dimensional just n non-interacting quantities. So that's one of the reasons diagonalization is important. And let me just interpret what's going on in the similarity a little bit more conceptually. Okay. So right now this is written as a sort of very algebraic fact. It's a factorization of A into this product. But what does it mean conceptually? So what does it mean to multiply, you know, sorry, there should be an X here, A by P dP inverse, right? Well, remember P inverse, so P is the matrix that contains the eigenvectors as its columns, right? Which are a basis. So this is the eigenbasis. And so conceptually, when you multiply by P dP, if you multiply X by P d to the K P inverse, what does this mean? Well, the first step, which is multiplication by P, is just you know, all it's saying is just express X in the basis of eigenvectors. So write X as some C1 V1 all the way up to Cn Vn. Okay, so the first step is just writing X in the eigenbasis. That's what happens when you multiply X by P inverse. The second step is multiplication by d to the k in this new basis. And so if you think about what that's doing, well, the point is when you write X in the eigenbasis, what it's doing is very simple. So by linearity, you can push the A to the K's inside. But now, because of the eigenvector property, these just become scalars. Okay, so when you express the vector in this eigenbasis, matrix multiplication becomes scalar multiplication. So taking a power of a matrix and multiplying just means you multiply each of these coefficients by the power of that eigenvalue. So this is step 2. And then what's the interpretation of step 3? Well, step 3 is you just now add all these back together to form the linear combination A to the kx. So A to the kx is now just, you know, equal to this linear combination. So that's a conceptual explanation of what this factorization means. It's just saying if you change your perspective to be this eigenbasis, then you can easily track what the powers are doing to these, to the coefficients of x, or to the coordinates of x in the eigenbasis. So any questions about this?
Is there a particular order that we have to write the eigenbasis for P? Like, for instance, do the vectors have to exactly line up to their eigenvalues in D? Does that question make sense?
Yes, very much. So the order of the eigenvalues, you know, in the beginning doesn't matter, but the first column, you know, of P has to correspond to the eigenvector from the first eigenvalue. If you remember how we derived this, that's actually really important. But as long as you have that correspondence, the order doesn't matter.
So let's say that lambda 1 has 2 eigenvectors in its basis. You can put both eigenvectors in either order, it doesn't matter, but as long as they're the first 2.
Exactly.
Okay,
exactly.
and the eigenvalues, they also don't have to be ordered in any specific order.
Yeah, they can be ordered however you want, but once you choose the order, the eigenvectors have to correspond to those eigenvalues.
Okay, thank you.
Yeah. Any other question?
What is the superscript k meant to indicate?
Well, I'm literally raising this to some power. It's just a number. So k is a large integer. I'm literally raising a to, like, let's say the 100th power.
Okay, thanks.
So the point I'm trying to make is that if you had a big matrix, it would not be so easy to raise it to the 100th power. But if you could diagonalize it, it would become easy. Okay. And
wait, sorry, I have a good question. So when you diagonalize a matrix, you're basically putting you're changing like the basis in which the transformation is occurring. Is that right?
You're changing the matrix. You're changing the basis with which you represent, with respect to which you're representing the transformation.
Right. So why don't you have to like change it back to its original basis,
You
I
do.
guess?
That's what P is doing, right?
Oh, I
P
see. So you're
inverse
changing
changes
the
to the eigenbasis. D to the K does stuff in the eigenbasis, and P changes back.
Oh, okay. I
This
see.
is
Thank you.
changed to eigenbasis. And this is, back from eigenbasis.
Okay, that makes a lot of sense. Thank you.
That's why you need P and both. You need P and P inverse. Okay, so I want to make one more remark. So in the skiers and borders example, there was one eigenvalue equal to 3/2 and one eigenvalue equal to 1. And as we took a large power, the 3/2 eigenvalue blew up because 3/2 to the 10 or whatever the number was is big, but the one eigenvalue didn't blow up. And so often in these dynamical systems problems, the eigenvalues have a very clear meaning, which I'll just say. So here's one interpretation of eigenvalues in dynamical systems. Well, if you have an eigenvalue with magnitude equal to 1, with magnitude bigger than 1, for example, the 3/2 that I had earlier, right? Then what that corresponds to is, so if I raise a to the k, right? That means I'm in this, if I apply a to the k to a vector, it means that eigenvalue is going to be raised to the k, right? And if the magnitude is bigger than 1, then this means, right, this means that a to the k has eigenvalue lambda to the k, and this is growing exponentially in k. So eigenvalues with magnitude bigger than 1 indicate exponential growth. Eigenvalues strictly less than 1 indicate, again, the same is true, but this is exponential decay. Okay, so what these numbers are telling us is that when you take powers, only the eigenvalues bigger than 1 end up mattering as k goes to infinity. Okay, so k is going to infinity. And okay, if you have an eigenvalue equal to 1, then no change. And if you have an eigenvalue equal to -1, then actually you have oscillation, right? Because a to the k times that eigenvector equals -1 to the k times the eigenvector. Okay, so this is a crude how to interpret eigenvalues in this context. And this is partly why eigenvalues are so important, because if you're interested in whether a virus is going to spread exponentially or something, that boils down to a question of computing an eigenvector of some matrix and deciding whether it's bigger than 1. Okay, so that's what I want to say about that. Any questions about this? Okay, so today I want to do 3 things. First, now I want to do eigenvalues and diagonalization of linear transformations. So not just matrices. Then I want to talk about complex eigenvalues. And then finally, I'm going to talk about some applications. Okay, so let's begin with this.
Quick question.
Yeah.
Is there a meaning if the eigenvalue is equal to 0?
That's a good question. So if the eigenvalue is equal to 0, What does that mean? It means AV equals 0, right? So it just means V is in the null space. Now, as far as so now in this dynamical systems context, taking powers is not really going to change anything, right? If you multiply by A once, it's going to be 0, and 0 to the K is just 0. So in this context, it doesn't mean anything that special, but in general, a 0 eigenvalue just means that there's a vector in the null space, which means the matrix is not invertible. But it doesn't really mean anything. I mean, it means something pretty boring in this dynamical context. Does that answer the question?
Okay, thank you.
Okay, so let's move on to eigenvalues of linear transformations. So far we did eigenvalues of matrices. Now let's generalize to linear transformations. So here's a definition. If you have a linear transformation from V to V, so again, it must be from V to V. This is the analog of having a square matrix. This is sometimes called a linear operator, which means V equals W. That's like a square matrix. It's an analog of a square matrix. Then X in V is an eigenvector of T if T of X, so it has to not be 0, if T of X equals lambda X for some lambda, which is called the eigenvalue. Okay, so it's the same definition. So now how would you compute the eigen vectors of a linear transformation? Well, I mean, you would get some equation here and you could just try to solve it using some sort of maybe abstract reasoning. Or you could turn it into a question about matrices. So how to compute? Well, how do you turn a linear transformation into a matrix? What do you need? What we need one more ingredient. What do you need?
Basis.
A basis, yeah. So how to compute? So choose any basis B of the vector space. And now observe. So now compute the basis of T with respect to that thing. So let A be the matrix, which is now this. So this is now a square matrix, right? This is n by n matrix. So assume V has dimension n. So assume there are n elements in this basis. And now, according to this like usual correspondence principle kind of reasoning, we have V going from T going from V to V, but now you have this basis. And now you can, just turn everything into a question about Rn. And down here you have this matrix A. And you know that this matrix satisfies A times the coordinate vector of B equals Tx, the coordinate vector of Tx. Or, maybe I'll just write this in the more suggestive notation. For every X in the vector space, right? That's what it means. But now the point is that, what does this mean? This means that lambda is an eigenvalue of T if and only if Tx equals lambda X, if and only if A times the coordinate vector of X equals lambda times the coordinate vector of X, which is if and only if lambda is an eigenvalue of A. Okay, so once you have a basis, you can turn eigenvalue problems for linear transformations into eigenvalue problems for matrices. And so this is true for any basis. It doesn't matter what the basis is. So just choose a basis and compute the eigenvalues of the matrix with respect to that basis. Let me do an example. But any questions before the example? Maybe I should call this like upshot or something, because this is like the point. Okay.
Can we explain what is the linear operator V equals to W?
A linear operator just means a linear transformation when it's just a linear transformation, but the domain is equal to the codomain.
Oh, okay.
It's just a new. This is just some new terminology. It's not a new concept. It's just new term. I mean, if you take physics and stuff, they'll use this a lot. It just means like a linear transformation from a vector space to itself.
Mm-hmm. Thank you.
So is this the same idea as before, except now we're, instead of going from like finding an eigenvalue for a specific vector, we're finding an eigenvalue for a change of coordinates basis?
No, we're not finding an eigenvector for a change of coordinates matrix. We're finding an eigenvector for the matrix of a linear transformation. Right. So this itself is this is the matrix of T relative to B.
So now we're finding eigenvectors for a matrix that corresponds to a transformation?
Yeah, yeah. This is just an instance of the correspondence principle again. Let me do an example just to make it clearer. So I have a linear transformation T from P2 to P2 by T of Q is equal to T plus 1 times dq by dt. So these are polynomials in the variable T. And I want to find eigenvalues and eigenvectors. Okay, so step one, just choose some basis. Let's just choose B to be the standard basis of P2. Step two. Oh yeah, sorry, choose a basis and write the matrix of, find the matrix of T. Okay, so fine, so I'm just gonna, okay, so this is T of the polynomial 1 with respect to this basis. T of the polynomial little t with respect to the basis. And if I do this computation, which I think we've done things like this many times, what you end up getting is first one you get 0. Makes sense because if you differentiate 1, you get 0. Second one, you get the polynomial t plus 1 that has coordinates 1, 1, 0. And the third one, you get 0, 2, 2. Okay, so that's the matrix. So find the matrix. And now step 2 is to find eigenvalues and eigenvectors of this matrix. So compute of this matrix. Let's just call it A to save notation. So, okay, what's the characteristic polynomial? Well, okay, it's an upper triangular matrix, right? It's particularly easy in this case. The matrix is upper triangular. So when I do determinant of T times T, this matrix minus T, I'll just get 0 minus T times 1 minus T times 2 minus T. And then it's obvious what the eigenvalues are. The eigenvalues are 0, 1, and 2. This is just or I could just say, you know, for upper triangular matrices, the eigenvalues is the diagonal entries. This is a general fact. Okay. So I found the eigenvalues of that matrix, and now let's find the eigenvectors. To use row reduction to find eigenvectors. Well, okay, so, you know, I don't want to do row reduction right now, so I'll just write down what they are. I get V1 equals 1, 0, 0. V2 equals 1, 1, 0. And V3 equals 1, 2, 1. Okay, so this is all stuff we did last week. This is not a new thing. The new thing is that now we're using this to find the eigenvectors of T. And that will now involve a third step, step 3, which is convert back to T. Convert back to P2. Right? Because what we computed are not the eigenvectors of T. We computed the coordinate vectors of the eigenvectors of T with respect to the B basis. And so the eigenvectors of T will be, let's call them x1, is going to be, I guess, PB of V1, which is just going to be the polynomial 1. X2 is going to be PB of V2, which is 1 plus T. And X3 is going to be PB of V3, which is 1 plus 2T plus T squared. And here PB is the isomorphism from R3 to P2. Which just takes a linear combination of the basis elements. And you know, indeed, and the eigenvalues are the same, right? Lambda 1 equals 0, lambda 2 equals 1, lambda 3 equals 2. And so you know, this actually checks out. You can check that these are the eigenvectors of T. They have to be. Okay, so it's just another instance of this correspondence principle. You turn it into a matrix, solve the problem for matrices, and translate it back. Any questions on this example?
So PB is not like strictly a matrix.
It's not a matrix at all.
Okay.
It's a linear transformation between R3 and P2. This is just a fancy way of saying you can turn everything into a matrix and do everything with the matrices. Now, there's one interesting thing here, which is the matrix that I get, A, right? That actually does depend on the choice of basis. And so it seems like, you know, in principle, the eigenvalues that I get from doing this could depend on which basis I choose. So let me ask this question. Do the computed eigenvalues depend on the choice of B? Any thoughts on that?
They should, right?
What did you say?
They should.
They should. Okay. It sounds like they should. Some people are saying no. Anybody have an explanation for why or why not?
Maybe you could treat the transformation as doing the same thing in any basis. It's just each basis is a different description of what it does. So it preserves like the same, or it has like the same eigenvalues.
Yeah, I guess
Like,
you're
it's the
coming
same
back
thing,
to this statement here, right? You're saying that whatever the eigenvalues are of t, they must be the same as the eigenvalues of a.
Yeah, I guess.
That's a good way to put it. This reasoning worked for any basis. And so whatever set of eigenvalues you get must be the same, right? Because of these are all if and only if. Whatever eigenvalues you get, whatever basis you got, those they all are equivalent to the eigenvalues of t. And so they must all be the same. That's a good explanation. Let me give you yet another explanation. So no. Let me give you a concrete explanation. So if C is any other basis of V, then the matrix of T with respect to C is actually related to the matrix of T with respect to B in a very specific way, right? Namely by these change of coordinates maps. But now I can write this as P, C gets B, this thing, times P, C gets B inverse. And so they're similar, right? Any two matrices you get from this are similar, and therefore they all have the same eigenvalues. So T and C, so T with respect to C and T with respect to B, the matrices are similar and have the same eigenvalues. Okay. And what's the point of this? Again, the point is the same, that you can now diagonalize this linear transformation, right? So we got these nice vectors here. Let's call this basis, I don't know. Let's call this basis C. So this is the basis 1, 1 plus t, and 1 plus t squared, right? x1, x2, x3. This is a basis of P2. And now what's the matrix of T with respect to that basis? So the upshot, when C is the eigenbasis, the matrix of T with respect to the eigenbasis is diagonal, as you would expect, right? So it's T of x1 in this eigenbasis all the way up to T of x3 in this example, which again by the eigenvalue equation is just going to be 0, 1, 2. Okay, so it's a general principle that the matrix of a linear transformation with respect to an eigenbasis is diagonal. So it's the same idea, just in the more general context. So general principle, the matrix of T with or relative to, I guess is the word the book is using, an eigenbasis is diagonal. And this really answers that question we asked a few lectures ago. What is the best basis with respect to which to describe a linear transformation? It's the basis of eigenvectors. So any questions about this? Okay. I mean, yeah. So for example, in physics, like this is what often happens, that you get some linear transformation from nature, and it doesn't come with a basis. And to really understand it, you have to find the eigenbasis, and that's how you understand it. That's like what a large part of quantum mechanics is about, finding eigenbases. Okay. Let me now move on to a different topic, complex eigenvalues. This is section 5.5 in the book. Now, the motivation for doing this is that, not all matrices are diagonalizable, right? So let's look at some examples. Example 1, let's look at this matrix. Rotation by 90 degrees. Its characteristic polynomial is t squared plus 1. This is not diagonalizable because there are no eigenvalues. So let's say not enough eigenvalues. Forget about eigenvectors. You don't even have enough eigenvalues. You don't have any eigenvalues. Here's another example. Let's look at this matrix. Characteristic polynomial is just t minus 1 squared. So you have eigenvalue equal to 1. But E1 in this case is just going to be the, well, okay, let's just calculate it. It's the null space of this matrix, which is the span of this vector. This is also not diagonalizable. In this case, you have not enough eigenvectors. Okay, so this matrix was a rotation by pi by 2. So complex eigenvalues is what we're gonna see is that there is a way to expand our notion of eigenvalues and even just of linear algebra to be able to diagonalize example 1. So we want to diagonalize more matrices, such as example 1. And this concretely is really important in physics, for example. Like, it really is important to diagonalize rotation matrices. And it's important in other areas of math. Now, the reason we're not able to diagonalize this is that there's this annoying equation that doesn't have any solutions, right? So what we're going to do is we're going to introduce complex numbers. So we won't be able to, there's no way to diagonalize this actually. So there's no way to diagonalize even with complex numbers. But we will be able to diagonalize the first example. So let me just say a bit about complex numbers. So let me give you a history of numbers. Okay, so numbers have been around for a long time. But we've actually had many different number systems. So the first number system was the positive integers, which is probably from, I don't know, thousands of BC, or it's probably very old. I don't actually know how old it is. And people were pretty happy with this for tens of thousands of years. But then there is a problematic equation in this number system. So namely, you could ask the following question: is there a number so that x plus 2 equals 0? You can ask that question if all you know about positive integers, right? Is there a number so when I add 2, I get 0? Or maybe, right, or let's say non-negative integers, right? So this forced people to expand the number system to create integers. And that was okay for a while. And then at some point, people realized that you can ask questions involving integers that don't have any answers in the integers, like this equation. Right, so you can easily, is there a number? So when I multiply by 2, I get 3. You can ask that question if you only know about integers. But it doesn't have an answer in the integers. So then, I guess in ancient Greece, they really got into this and they decided to invent, or I don't know if they invented it, but they at least wrote about it a lot, the rational numbers, which is fractions. And this people were pretty happy with until I think about 200 BC, or maybe even a little later. But there are some very problematic equations in this also, like x squared equals 2. And this actually was like, the existence of this equation was some kind of a guarded secret. And there was somebody, I think it was Pappus, who publicly talked about this in 200 BC and was thrown off a ship or something. So they were very bothered by this fact that you could write down equations that didn't have solutions. And then finally, people invented the real numbers, which include the irrational numbers. Okay. And then x squared equals 2 has a solution, right? Namely square root of 2. Even though you really it requires a bit of a leap, right? Because you can't actually write down the square root of 2, but you can still talk about it as a well-defined number. And this lasted for several hundred years, but people were always bothered by this. And this is the equation that around 1600 AD, due to work of Cardano, led to the introduction of complex numbers. And complex numbers, include this unfortunately named number called I, which is the square root of -1, which has the property that I squared is equal to -1. And it satisfies this equation. And what's really special about the complex numbers, it's unfortunately named because people think there's something not real about them, or that there's something sketchy about them, or that there's nothing imaginary about complex numbers. They're just as real numbers, if not more real, according to me. I'll say more about that in a moment, but the punchline here is that there are no problematic equations. Okay, so this is really the end of the line. Now, as was just brought up, there's this philosophical, I was wary of complex numbers myself for a long time. Because, somehow there's this philosophical question, which is, are complex numbers real? Okay, and they have this sort of a bad reputation as somehow being on less of a firm footing as real numbers, but that's really not true. Yeah, numbers are just a mathematical construct. That's right, as somebody is saying. So this is a useless question. Useful question is, are they a useful concept for describing nature? And the answer is yes. They're much more useful than, yeah, they're amazingly useful. In fact, we don't know a way to describe nature at some level without them. So let me just tell you what complex numbers are. Here is the definition. So just out of curiosity, how many people have not seen the complex numbers before? Has anybody not seen them? No need to, it's not a prerequisite, so I'm just trying to gauge. Has everybody already seen complex numbers before? I'm trying to judge how quickly to go. Okay, I'm just getting a lot of yeah. So let me just quickly review what they are. So it's a set of numbers of type a plus ib, where a and b are real numbers. In particular, the set includes the real numbers by setting b equal to 0. And if you have a complex number z equal to a plus ib, then a is called the real part and b is called the imaginary part. So they're defined by pairs of real numbers. And then you can add, multiply, and divide them. So a plus ib plus c plus id is a plus c plus ib plus d. You can multiply them, and this is where things get interesting. You just multiply them using the usual rules of algebra that you're used to. So use this, FOIL or whatever it's called, and you get AC plus IAD plus IBC plus I squared BD. And now you use this key property that I squared equals -1, and you get that this is AC minus BD plus IAD plus BC. Okay. And then you can even divide them. The way to divide them is if you have a plus ib and c plus id not equal to 0, the way to reduce it to multiplication is you can multiply and divide by c minus id. So this is an important operation called the conjugate. So the conjugate of a plus ib is a minus ib. And you have the important property, if you do this multiplication, that when you multiply a number by its conjugate, the imaginary part, the product has no imaginary part. So if you do this multiplication, you just get, let's see. So I guess you get AC plus BD plus BC minus AD over C squared plus D squared. So you need C squared plus D squared to not be 0. So you need the number to not be 0, right? Can't divide by 0. So you can do the usual algebraic operations with complex numbers. Certainly you can do subtraction. And okay, you can do absolute value of z. So this corresponds to a picture. So there's a complex plane where you have the imaginary axis and the real axis and the imaginary axis. And a complex number, a plus ib, is just, it's like you can think of it as a vector in this with coordinates a and b. And so then the magnitude is the length of this line, which is by the Pythagorean theorem, a squared plus b squared. So those are the complex numbers. And there's a lot more to say about them, but that's the basics. And arithmetic works the same way, except for this important equation, star. So all the familiar rules of arithmetic apply: distributive law, associative law, et cetera, et cetera. So any questions about this crash introduction to complex numbers?
What is that, like c unequal to 0 in the dividing line?
Oh yeah, so you have to divide by something that's not equal to 0. It's not c, it's the whole number. Yeah, you can't divide by 0. Okay, so the upshot, yeah, please, another question?
Yeah, I've always wondered this about complex numbers before. So I understand this like image, and I've seen it before of the graph where there's this like graphical, the triangle representation of like a plus bi. But we don't represent, let's say, the number 5 by using 2 plus 3 on a Cartesian plane. So why is the complex number using a Cartesian plane to represent? Does that make sense?
It makes sense, yeah. So the reason is that when you multiply 2 plus 3 by 4, that's the same as multiplying 5 by 4, right? You don't need to know, like 2 plus 3 is the same as 1 plus 4 is the same as 3 plus 2. for all purposes of arithmetic, right? But for complex numbers, 2 plus 3i is not the same as 3 plus 2i, right? When you multiply something, the imaginary part behaves differently from the real part. So you have to keep track of them separately.
Okay, thank you.
Yeah, somebody's making a great point. Isn't it kind of like adding vectors? So you're right. This is kind of like R2, right? You're right. It is kind of like R2. What's the difference between this and R2? Why do I need a new concept here? Somebody want to say? People are saying different bases, saying one dimensional. No, it's more basic than that. Yeah, we don't have multiplication in R2. Okay, so a vector space is not the same thing as a number, as a space of scalars, right? You can't multiply vectors. But in complex numbers, you can do everything you can do in real numbers. Okay, now the point is that everything we learned for example, linear combinations, span, row reduction, all that stuff still works if you use complex scalars instead of real scalars. Okay, so this is not something we're going to do too much in this course because it's not really something I want to emphasize. But it will come up later on in many of your other courses, so I want to just introduce you to it. So here's a definition. We'll only do this in this lecture, and the rest of the lecture will go back to real vector spaces. You can define this vector space Cn of complex vectors with n entries, and the operations are the addition is defined the same way. But scalar multiplication is more general, because you can multiply by complex scalars. Okay, and everything actually still works. We could have done the whole course with complex numbers, and nothing would have actually changed. So this is Cn. But why are we developing this sort of new framework of linear algebra with complex scalars? Well, the main new thing that happens is you have the fundamental theorem of algebra, which I stated earlier, but I'll just restate. If P of t is a degree n polynomial with complex coefficients, so what that means is P of t is equal to some a naught plus a1t all the way up to a n t n, t to the n, then P has exactly n complex roots, lambda 1 through lambda n with multiplicity. So what that means is that you can always factor completely. So this problem of not having enough eigenvalues just goes away. And so the consequence of this is that an n by n matrix always has n complex eigenvalues. An n by n, let's say, real matrix, or it's even true with complex, an n by n complex matrix has exactly n eigenvalues counted with multiplicity, right? Because the characteristic polynomial is of degree n. So let me demonstrate this with an example. But any questions so far? Okay, let me do an example. Just example 1, the same one we saw earlier. You have A being this rotation matrix. And the characteristic polynomial is t squared plus 1, which factors as t plus I times t minus I. So this is the new thing. And so the eigenvalues are plus I and minus I. And what are the eigenvectors? Well, let's calculate them. So the eigenspace corresponding to plus I is the null space of A minus I times identity, which is the null space of, so A is this matrix, I times identity is this matrix. And this is your first real encounter with complex linear algebra. You now have to row reduce this matrix, right? So it's a null space of I minus 1, 1, I. And so let's row reduce it. Well, the pivot is this, right? So just follow the rules. Don't freak out just because it's complex. Just follow the rules. What do? You zero out the entry below the pivot by subtracting an appropriate multiple of row 1. So you do R2 gets R2 minus R1 divided by I. So now, okay, you have to do some arithmetic, right? So the first row doesn't change. 1 minus I over I is 1, this becomes 0. But now you have to calculate minus 1 over I, right? So what's minus 1 over I? Or maybe in this case, yeah. So this will be I minus minus 1 over I, right? So what's minus 1 over I? Well, I showed you to do division, you just do this trick where you multiply and divide by the conjugate. So it's multiply and divide by minus I.
Oh wait, Professor, sorry. This has been said in the chat, but why isn't it negative I if it's 0 minus I?
Wait, 0 minus I?
You have null of 0, negative 1, 1, 0 minus the identity of I.
Sorry, yeah, minus I. Whoops, thank you. I would have computed the other one, but okay. So okay, let's put negatives everywhere. Fine. Thanks. Yeah, negative I. And so then you divide by negative I, R1 by negative I. There are a lot of negative signs around, but okay. You have minus I minus negative 1 by negative I. Okay, so what's negative 1 by negative I? Well, now, okay, the conjugate is this. You get minus I divided by minus I squared. Minus I squared is just 1, so minus I. You do this little calculation here with complex numbers. And so you get that this is I minus 1, 0, negative I minus negative I, which is also 0. And so this is now a pivot. This is a free variable. And so the null space of this matrix, let's call this star, is it's the set of all vectors x1 and x2 in C2, so that Ix so that Ix1 minus x2 equals 0, right? That's the equation you get, and x2 is a free variable. So this is just x2 is free, so it's just a span of, well, let me just write it out carefully. It's a set of all vectors of type Ix. X1 is x2 divided by I. So x1 is x2 divided by I. 1 over I is, okay, let's do it here. 1 over I is just minus I. So it's just x2, this is minus I. x2, where x2 is in C. And this is the span of the vector minus I1. But now I'm going to emphasize that the span is with respect to complex scalars, okay? So span sub C, which means you're allowed to take complex linear combinations. Okay, so that's the eigenvector I computed. Let me just check that I haven't messed up some signs here. So this is minus I. Oh, sorry, there was a minus here all along. I'm sorry. Okay, minus here. So then this goes away. This just becomes Ix2. And this just becomes I, 1. And let's just check that this indeed worked. Well, this matrix minus 1, 1 times the vector I, 1 equals the vector minus 1 I, which is actually equal to I times the vector I1. So yeah, this is a legit eigenvector. Okay, so let's call this eigenvector V1. It's a complex eigenvector living in C2. So any questions about that computation? We computed an eigenvector using the same method. Method isn't different. But you just have to do a little bit of complex arithmetic. Okay, so same method as before, but with some complex arithmetic. Okay, and what about the other eigenvector? So similarly, you can compute the other eigenvector V2, which turns out to be minus I1 with A V2 equals minus I V2. But there's actually a shortcut here. So this is a general fact that comes up when dealing with complex matrices. So the general principle, so the pattern here is that this vector V2 is very similar to V1, except I just flipped the sign on the I, right? And in fact, the eigenvalue is also the same as lambda 1, except I flipped the sign on the I. And that's not a coincidence. So generally, if you have a real matrix, if A is real, and AX equals lambda X, then A times X conjugate equals lambda conjugate X conjugate, where X conjugate is the vector with every entry conjugated. You can just check. This is just because equations that are true about complex numbers remain true when you take the conjugate of both sides. And if you know complex algebra, the conjugate of the product is the product of the conjugates. Okay, so this is just because you conjugate both equations. And the reason, so we use that A is real because A conjugate is equal to A.
Wait, so just to clarify, the bar at the top is notation for conjugate?
That's right. So this bar notation means a complex conjugate. Entry-wise. So you apply the conjugate to every entry. And so in general, if you have a real matrix, and in this course, we'll almost always be looking at real matrices, the complex eigenvalues come in conjugate pairs. So there is one nice thing, which is once you compute one of them, you get the other one for free. Right? So the conclusion is that lambda is an eigenvalue if and only if lambda bar is an eigenvalue. So this is a general pattern for complex eigenvalues. Now you might wonder, so okay, so if you now do this whole thing, you can diagonalize matrices. You can diagonalize a lot more matrices. You just have to allow P, D, and P inverse to now be complex. So the upshot is you can now diagonalize a lot more matrices. Okay. Now, what is the meaning of complex eigenvalues? Well, I'll just state one theorem from the book. Theorem is just for 2 by 2 matrices. The theorem is if A is a real 2 by 2 matrix with eigenvalues A plus IB and A minus IB, and those have to be the eigenvalues because they're conjugate pairs. Then A is similar to a matrix C, which is not diagonal, but it's a matrix we can interpret. For C given by this matrix, A, B minus B, A. So that's a special structured matrix, right? The 4 entries aren't just anything, they have a specific structure. And you can write this as a rotation matrix. So if you write A as R cosine theta and B as R sine theta, so you can always do this by drawing a little triangle, right? If you do this change of variables, then this is just this number R times a rotation matrix. So this is rotation by theta, and this is just scaling by R. And this R is, just equal to square root A squared plus B squared. So the meaning is, this is it's not a complicated proof, but I don't really want to dwell on it in the course. This is meant to just be an introduction to complex eigenvalues. So the next time you see them, you're a little more familiar. But roughly the meaning is it's rotation. Okay, so example 1 was a rotation. It had complex eigenvalues. This theorem says whenever you have a pair of complex eigenvalues, there's some rotation going on. So you can read about this in the book. I mostly just want to state this theorem rather than just for interpretation purposes. But any questions about this theorem? So the proof is in the book. Okay, so that's all I want to say about complex eigenvalues. And let me show you one application before the lecture is out. The application is to search engines. So search engine is, I guess, something we use all the time. It's a software that's given a query. it returns a list of relevant web pages. Sorted by importance. And the sorted by importance is very important because the internet has a lot of web pages, and the whole point is to rank them correctly, right? So the history of search engines is the following. So until 1997, there were a bunch of search engines around. For example, Alta Vista. I don't know, Lycos. Have people ever heard of any of these search engines? I'm curious. Anyway, there used to be a bunch of search engines. And they were based on this idea that the importance of a web page should be proportional to the importance of the words in the web page. And okay, I don't know if anyone was using the internet back then, but it was considerably worse, the results you got from this approach. And then in 97, 98, there was a new search engine, or there was a startup called Backrub, which had the following nice idea. The idea was that the importance of a web page should be proportional to the importance of the web pages linking to it. Okay, so this sounds circular, right? You're defining importance in terms of itself. You're saying, you are important if other important web pages think you're important. Okay, so this is axiom 1 of this Backrub. And let me just explain. So they followed this, and let me just explain exactly what mathematical model they got. So here's a sort of micro internet. So suppose you have 4 web pages labeled 1, 2, 3, 4. And let's suppose these are the links between them. So an arrow means some web page has a link to some other web page. Okay, so this is just some example. This is like a tiny version of the internet. Now, axiom 2 of this idea was that you should weight the links according to, so the weight of a link should be equal to 1 over the number of links on the source web page. Okay, so this is because in the early days of the internet, a lot of people tried to boost their search results just by making lists of links. So you'd have a web page with like millions of links on it. And obviously that should be discounted. So what I'm going to do is I'm going to label these links by the number of links on the source. So let's look at all the arrows coming out of the first web page. So there are 3 of them, right? 1, 2, 3, and they're all going to be labeled 1/3. And then the second one, there are, I guess, there's just 1, so it's going to get a weight of 1. The third one, I guess there are 2 links, so they'll both get a half. And the fourth one, they're also 2, so they both get a half. Okay, so these are 2 simple rules. And now let's see if we can calculate the importance using this. So let's define an importance vector, x1 through x4. And the rules say that the importance of a page is proportional to the sum of the importance of the web pages linking to it. And we're going to interpret that as being the sum, right? So x1 is proportional to, so x1 has, what are the incoming arrows for x1? Well, just x2, right? So x1 is proportional to x2, and I'm going to call the constant of proportionality lambda. Right? Because the first web page has only one link coming in, and that's from x2, and that gets a weight of 1. Second web page here has 2 coming in, 2 links coming in from x1. So you have a third times x1 plus a half times, oh no, actually it has 3 coming in plus a half times x3 plus a half times x4 times lambda. X3 is, I guess, has 2 links coming in. It has a third times x1 plus a half times x4 times lambda. And lambda x4 is equal to, I guess it only has 2. So it has a third times x1 plus a half times x3. So these are some equations. And the point is that this is just an eigenvector equation. Right? This is equal to, if you write these in a matrix, this is just an eigenvector equation. And okay, if you write, okay, I mean, yeah, so you have 0, 1, 0, 0. And then for x2, I guess you have a third, 0, half, half, etc., etc. This is an eigenvector equation. And you can solve this, and you get a solution with lambda equals 1 and x equals some positive vector, which turns out to be 12, 4, 9, 6. And you use this to give the ranking. So according to this, you know, the most important web page here is number 1. Second one is number 3 because it has the second highest value. The third one is number 4. And the last one is number 2. Okay, so there's a theorem saying that this such a matrix always has a unique eigenvector with lambda equals 1. And all the entries are positive. And so this is actually the key idea behind this backrub, and this actually was renamed to Google. So this was the original paper that started Google, and this method is called Pagerank, and it's actually what we use. It's actually what we use to rank web pages. So, you know, the single most important event in search was the realization that the right way to think about search is it's an eigenvector problem for the whole internet. Of course, okay, there's this question that how do you compute the top eigenvector of the internet? It's a really huge matrix, right? The answer is you can read section 5.7 to give you some idea, but you need some methods more than what we've done. Anyway, any questions? So some people asked some questions in the chat. Please, you can ask them now if you want.
So is that why Wikipedia is always like one of the top websites that's listed when we search up for a topic because it has so many links that cite it and links that it cites?
Yeah, more importantly, it has many links that cite it, and those links are those things that cite it are considered important. They're not just some like clickbait kind of websites, right? So I mean, literally, yeah, what it's saying is that if you were to use these 2 axioms and compute the eigenvector for the internet, the Wikipedia entry would be very large.
Okay.
Yeah. So this is another way eigenvectors come up a lot in practice, that you can, if you want to define something in terms of itself, or you want to define you know, what happens at somewhere in terms of what happens at the neighbors, naturally that's an eigenvector equation. But yeah, somebody else had a question?
Yeah, how can we make sure that such a matrix will only have one unique eigenvalue?
This is a theorem, so we won't prove it in this course. But you can prove that if you make a matrix this way, so it'll have many eigenvalues, but it'll only have one eigenvalue equal to 1, and the
Oh.
eigenvector for that will have positive entries.
Okay.
So this is, well, we will not prove this. If you take, I think, stat 134a, they may prove this theorem there. Or if you take probably CS, maybe even 70 or maybe 170, they'll prove theorems like this.
So it says it will has a unique eigenvector for the eigenvalue equal to 1.
Yeah. The theorem is if you make a matrix like this out of any collection of links, 1 will be an eigenvalue, and it will have exactly one eigenvector, and actually all the entries in that will be positive, and therefore you can use them as a ranking vector, right? So this gives you the ranking. Okay, so I unfortunately have to run to go to a panel now, but so I can't stick around, but yeah, see you next time.